Hello, this is FlippedHarber for Algebra 2. In this video we'll be covering section 6.6, the fundamental theorem of algebra. Our objectives for this lesson are to use the fundamental theorem of algebra and its corollary to write a polynomial equation of least degree with given roots. We also want to identify all the roots of a polynomial equation. The outline for this video, we'll start by writing a polynomial given the zeros. We'll talk about the fundamental theorem of algebra. We'll look at finding all the roots of an equation with the help from a graph. We'll look at the complex conjugate root theorem. We'll look at writing a polynomial with complex zeros. And then we'll end with finding all the roots of an equation. Now, writing a polynomial given the zeros means that they're going to tell us the zeros, what numbers x should equal in order to solve the equation or to make the polynomial equal 0. And then we need to, from those zeros, create the corresponding factor. So I need you to remember from previous sections that for every factor there is a root. Well, now we're going to work that backwards and say for every root or zero there is a factor. Now let's go ahead and use an example where they tell us that x equals -2, 1, or 3 are the zeros of the polynomial, or the roots of the polynomial. From each of those roots, we create a factor. So the root -2 creates the factor x plus 2, the root 1 creates the factor x minus 1, and the root 3 creates the factor x minus 3. Now our job is simply to multiply all of these together. We get f of x equals x cubed minus 2x squared minus 5x plus 6. I expect that you should know how to multiply those binomials together. Now, in some of your examples, they're going to give you irrational numbers, that is, square roots. You need to remember the rational roots theorem, which basically says that if you're going to have nice numbers for coefficients, then your irrational roots occur in pairs. So they're only going to tell you one of those irrational roots. You have to know to add the other one. So if they tell us that x equals -2, 1, and the square root of 3 are all roots of the polynomial, we need to know that we're actually going to make two factors using that square root of 3. One for the positive square root of 3 that they give us, and one for the negative square root of 3 that we're supposed to know about. So our four factors are x plus 2, x minus 1, x minus the square root of 3, and x plus the square root of 3. Now if you go ahead and FOIL the first two binomials, and then either FOIL the last two binomials or treat them as a difference of squares, we're well on our way to finding the polynomial. All we need to do is multiply and combine like terms, and we get the polynomial f of x equals x to the fourth plus x cubed minus 5x squared minus 3x plus 6. Again, I expect that you know how to multiply these polynomials together. Now, the fundamental theorem of algebra states that every polynomial function of degree n greater than or equal to 1, that means that it's got a polynomial with a variable, has at least one zero, where a zero may be a complex number. Now, there's a corollary to this that says that every polynomial has exactly n zeros, including multiplicities, meaning if n is 2, it's a quadratic polynomial. It definitely has two zeros, but both of those zeros might be the same number. It has a multiplicity of 2. Now, let's take a look at these two polynomials. The first one will have 3 zeros. Some may be repeated, now that's the multiplicity. Some may be irrational. If there are irrational ones, they would have to come in pairs based on the irrational root theorem. Some may be complex. We'll talk about complex zeros in a little bit. The g of x will have 4 zeros. Again, some may be repeated. Some of them may be irrational. If there are any irrational, they come in pairs. And some of them may be complex. Now, let's take a look at finding all the roots of an equation with the help from a graph. Really what I want to do is my p over q stuff. My p values are plus or minus 1, 2, 4, and 8. My q values are only plus or minus 1. So my P over Q are plus or minus 1, 2, 4, and 8. If we take a look at a graph for this function, it appears to pass through the x-axis at 1 and negative 2. So this means we should try these numbers first. We're either going to confirm them or show that they don't actually go through 1 and negative 2. Now, synthetic division is a great way to try this. Remember, we can find out if negative 2 is a root or a 0 by synthetically dividing by negative 2. So as we go through the synthetic division process, we find out that the remainder is 0 with negative 2. So yes, negative 2 is a root or a 0 of the polynomial. Let's try 1, not all over again. Let's try 1 on this depressed polynomial. So I do my synthetic division on the 1, negative 1, 4, negative 4. Not on the original, but on the depressed polynomial. Again, I get 0. So yes, 1 is also a 0 or a root of the polynomial. And now the polynomial has been depressed all the way to a quadratic. 1, 0, and 4 are A, B, and C for a quadratic polynomial. Now, I set that equal to 0, or I could use the quadratic formula to find this, and I get x equals plus or minus 2i. So 2 imaginary roots. So my 4 roots are plus or minus 2i, negative 2, and 1. Again, I knew that there would be 4 roots total because the highest power on x is 4 in this polynomial. Now let's take a look at the complex conjugate root theorem. It says that if a complex number is a root to a polynomial equation with real coefficients, then the complex conjugate is also a root. So complex number roots occur in pairs, just like irrational roots occur in pairs. Those pairs are complex conjugates. Now, if we want to write a polynomial with complex zeros, just like earlier, we need to remember that complex roots or complex zeros occur in pairs. So you need to know to add the complex conjugate to our list of zeros or roots. So if they tell us negative 1 and 2 plus I are 2 roots of a polynomial, we need to add 2 minus I as another root. So I create my factors, x plus 1, x minus 2 plus I, and x minus 2 minus I. Again, I need to know to add this complex conjugate as a root and create its factor. So I like to start by multiplying my complex factors together. So I FOILed these last 2. I don't know where that all went. But as I multiply things out and combine like terms, these imaginary numbers are going to cancel out. Okay, so let's find all the roots of this equation. Again, this is a special case. We're going to actually factor this like a quadratic. You've seen me do this before, but obviously this one's special. As I factor it out, I have x squared plus 4 and x squared minus 3. Now I'm going to set each of these equal to 0 separately. Solving for x, I get x equals plus or minus 2i, so I get a pair of complex roots, and I get x equals plus or minus the square root of 3. I get a pair of irrational roots. Okay, that's it. So now it's time for you to try some of this on your own. I'll see you in class and I'll see you online.